Welcome to the Explainer. Today we're doing something a little different. We're going to take a university physics assignment and use it to decode the powerful language of vector calculus. I mean, this is the language physicists use to describe all the invisible forces shaping our world, and we're going to break it all down together.
So it really all kicks off with a fundamental question, right? We all feel gravity, we've seen magnets work their magic, but how do you actually describe that? How do you put a map to something you can't even see?
And the answer to this question, well, this gets to the absolute heart of the matter. It's not just about how fast you're going, but which way you're going. That single tiny addition, direction, is the fundamental building block for this entire field. It's huge.
And here it is, laid out plain and simple. On the left, a scalar. It's just a number. 50 miles per hour, 20 degrees Celsius. Super simple, right? But on the right, a vector adds that one crucial piece of information, direction. 50 miles per hour times north. That's not speed anymore, that's velocity. And believe me, that one little distinction, it changes everything.
All right, so let's get our basic vocabulary down. We're going to pull some formal definitions straight from our source assignment to get started.
So first up, we've got the scalar quantity. The assignment tells us it's just a quantity with magnitude. Think about the examples here: speed, distance, energy. These are the numbers you use every single day. They tell you how much, but they give you absolutely no clue about which way.
And then, on the other hand, you have vector quantities. Now these have both magnitude and direction. Just look at the examples. Weight is a force, and it's always pointing down. Momentum has a clear direction of travel, a magnetic field. It's always pointing somewhere, right? From one pole to the other. These aren't just numbers anymore. They're basically arrows.
Okay, now this is such a cool idea, the unit vector. Think of it as pure distilled direction. It completely strips away the how much and only answers which way. Its length is always exactly 1, so it never messes with the size of anything you apply it to. It's just a perfect little pointer, an absolutely crucial tool for physicists.
So here's the really important part. These arrows, these vectors, they're not just some fuzzy concept. They have rules. They've got their own algebra, like a grammar, that lets us actually work with them, combine them, and solve real problems.
And we can actually visualize how this whole thing works. Take a problem like RMN plus RMP from our source material. That's not just a bunch of symbols on a page. It's asking a real question. If you have a force pulling from point M to point N and another force pulling from M to P, what's the combined result? You can literally draw those arrows, stick them head to tail, and find your answer. It's this really beautiful geometric process.
So we can add individual arrows together. Big deal, right? But what happens when we zoom out, way out, and imagine a whole universe of them? This next idea, this is the big conceptual leap. This is what lets us finally map those invisible forces we were talking about right at the start. Okay, this right here, this is the single most important idea in this entire explainer, so really let it sink in. Forget one arrow, or two. What if there was a vector at every single point in space? An infinite grid of arrows filling this room, the ocean, the space between planets. What would that even look like?
Well, that is what we call a vector field. And just like that, suddenly we have a way to describe the flow of wind in a hurricane, where every single molecule of air has its own speed and direction. Or the gravitational field around the Earth, where every point in space has a little arrow pointing right toward the center. We're not talking about one arrow anymore, we're talking about a whole invisible landscape of force and flow. And this is what a vector field looks like when you write it down in the language of math. This equation is pulled straight from the assignment, and it's not just a jumble of letters, not at all. It's a recipe, a formula. You give me any point in space, an x, y, and z coordinate, and this recipe will spit out the exact arrow, the exact vector, for that one specific spot. It's a complete map of an invisible world.
All right, so we've got this incredible invisible map. But a map's no good if you can't read it, right? How do we actually decode the patterns hiding inside this universe of arrows? You know, the sources, the swirls, the hills and valleys.
Well, the way we do it is by using these special mathematical lenses. Seriously, don't think of them as scary equations. Think of them as different kinds of glasses you can put on to look at the field. Each lens is designed to ask a very specific question, to reveal a different characteristic about what the field is doing at any given point.
And here are the three big ones from our assignment. First up, you've got the gradient, or grad V. This lens asks the question, which way is uphill and how steep is it?
Imagine you're standing on a hillside. The gradient vector points you up the absolute steepest path. Then there's divergence, or div-A. This one asks, is stuff flowing out of this point or into it? Is it a source, like air blasting from a vent? Or is it a sink, like water going down a drain? And finally, you have the curl. This asks a simple question. Is the field spinning or rotating right here, just like a whirlpool? So really, we're just asking about slope, flow, and spin. That's it.
Okay, I know this can all feel pretty abstract, like some kind of game for mathematicians, but I promise you, this language, it's the hidden engine that powers so much of our modern world.
And here's the proof. This math is not just on a chalkboard. Vector fields are how we model gravity to keep satellites in orbit. The curl we just talked about, that's essential for modeling the airflow over an airplane's wing to generate lift. Divergence? That helps engineers understand how heat flows away from a computer chip to keep it from melting. And those coordinate systems? That's the literal foundation of how your GPS pinpoints your location. This stuff is everywhere.
Because at the end of the day, that's what vector calculus really is. It's this incredibly elegant and powerful language that we invented. It gives us the words, the grammar to describe and predict all those invisible forces that govern our universe. The pushes, the pulls, the flows, the swirls, everything that's happening around us all the time, from the tiniest particles to the biggest galaxies.
And that's our quick tour. So, I'll just leave you with this final thought. The question on the screen. If you could suddenly see all of these vector fields around you, the flow of heat from your coffee, the pull of gravity on everything, the swirl of the wind outside, what patterns would you look for first? Thanks for joining us on The Explainer.